All right, guys, let's get started with reviewing this one together. So our first question, what type of bond do all the molecules in the table on the right have in common? So first off, even if you're not sure, this word right here, molecules, that should tip you off that it is going to be covalent as your answer, because you can only use that word molecules when you talk about compounds that are bonded through the sharing of electrons. So sharing of electrons is covalent. Another way that you could answer this one is all of these compounds consist of only nonmetals. Okay, so you have a Brinkelhoff, then you have nitrogen and hydrogen, and you have carbon and hydrogen. All of these are nonmetals. If it's only nonmetals, then it's going to be covalent. All right, so we talked about numerous times that ionic is metal and a nonmetal, covalent is nonmetals only. So the fact that these are nonmetals only and that the word that is molecules is used should tell you that. Number 2, how many pairs of unshared electrons are found around the central atom for phosphorus trifluoride, PF3? If you draw out phosphorus trifluoride, we're talking about, excuse me, 26 total electrons to work with, 21 from the fluorine, and another 5 from the phosphorus. And remember, I just based that off of this right here. Phosphorus is in group 5A, fluorine's in group 7A. So we're talking about 26 electrons to work with. You would put phosphorus in the middle because it's least electronegative. You would form single bonds to all your fluorines. You would fill all the octets for your fluorines, giving each one 6. At that point, you've only used 24 electrons. You have 2 more left, and hydrogen needs 2 more to be happy. So you're going to put a lone pair on hydrogen. All right. So it's asking you how many pairs. It's going to be 1 pair on hydrogen. Okay. Sorry. A lot of y'all chose 2 as your answer right there. Yes, there are 2 electrons, but there's only 1 pair, and that's what the question was asking you for. All right. How many valence electrons are found within the carbonate ion? So again, here you just have to add. So CO3 2-. So carbon is in group 4A, it's bringing 4 valence electrons. Then oxygen's in group 6A, and you have 3 of them. So 6 times 3 is 18. So 4 plus 18 is going to be 22. And then this -2 charge on the carbonate tells us we have 2 more electrons. So altogether, we have 24 total electrons in this particular compound. There we go. Which of the following properties is not explained by the electron C model of electrons and metals? So remember, the electron C model involves electrons just floating around randomly within the space of the metal, and they can go anywhere they need to, from island to island, we like to say, because they're like fish in the sea, and your islands are just your positive nuclei. So electrons can go from spot to spot to spot to spot. They're not held any one direction. Now, having said that, even if you didn't know that, you have got to know that this is the wrong answer, okay? Because it's asking you which of the following properties is not explained by the electron C model in metals. So in other words, if you're not even sure what electron C model is, you know we're talking about metals. And you know that metals are good conductors of heat and electricity. So if metals are good conductors of heat and electricity, it doesn't even matter why. This has to be it has to be the answer that doesn't make any sense, okay? The one that says that they are poor conductors of heat and electricity. Again, you don't even have to know what the electron C model is to know that. You just need to realize, hey, this is not a true statement of metals, therefore it's got to be the right answer. Okay, we've got to do a better job of reading our questions and really analyzing the answer choices we have. But because those electrons aren't attached, you can shape metals, bend them, and shape them into what you want, which is malleability. Those electrons jump to excited states and then fall back to ground state. That's what gives them shininess or luster. Again, because the electrons aren't held tightly, you can pull metals into long wires. And it just makes sense that if electrons aren't held tightly by one particular nuclei, then they're very easily given away. Number 5, according to the VSEPR model, why do you see a decrease in bond angles of these molecules right here? So again, this is something that we did almost exactly in the pair deck review. Okay, I designed a question to look just like this, so you have to be able to translate that information. So CH4 is tetrahedral. That's going to have a bond angle of 109. Okay, and it's not like I have that memorized per se. Tetrahedral, 109.5. And then we have NH3, which is going to be trigonal pyramidal. Okay, you have a lone pair on the nitrogen. So that's pretty much 109.5 as well. So they're pretty close together. All right. And then finally you have water. Okay, so you're going to have 2 single bonds and 2 lone pairs. So water is bent. All right, so that is going to be this guy right here. Okay, and well, actually, water is going to be a little bit different than this one right here. The bond angle for water is going to be 104.5. Okay, so it's actually going to get a little less than this particular chart. All right, but either way, okay, this is going to be your greatest bond angle in tetrahedral, and then trigonal pyramidal has a slightly smaller, and then bent has a slightly smaller. Okay, if you think about lone pairs, tetrahedral doesn't have any, trigonal pyramidal has 1, and bent has 2. That is the reason that the bond angles change. We talked about the fact that lone pairs are more repulsive than bonding pairs. They have more repulsive power. So the more lone pairs you add to a compound, the further they're going to push the bonding pairs down, which is going to cause a decrease in bond angle. Okay, so your correct answer is D. Okay, it's the increasing the number of unshared or lone pairs of electrons. The more lone pairs you have, the more repulsion they have, the more they're going to push the bonding pairs down and create smaller angles. All right, for 6 and 7, we have these compounds right here. So you have CBr4, which is tetrahedral, PCl3, which is trigonal pyramidal, NH3, which is also trigonal pyramidal, CO32-, which has a double bond, so that's going to be trigonal planar, and HCN, which has a single and a triple, but it forms a linear compound. So it asks which one of these contains a double or triple bond. Okay, well remember the only ones that can form multiple bonds are cons. So you're looking for a compound that has C, O, N, or S. Okay, and it can't really just have one of those. It's going to have multiples of those. So we have a C here, but that's it. That one doesn't work. We have an N here, but we know H can't bond more than once. We have a C and an O here, so 2 of the cons. And like I said, you're going to have a double bond between carbon and one of the oxygens. Then HCN, again, you have 2 of the cons. You're going to have a triple bond between carbon and nitrogen. Okay, so these 2 right here, 4 and 5, are going to be the ones that will form multiple bonds. So again, you got to remember cons, C-O-N-S, they're the only ones that can form multiple bonds, and they're going to have to be at least 2 of them, okay? You can't just have one of your cons in a compound because then it won't have anything else that it can form a multiple bond with. And then number 7, which is above has 32 electrons, so you just have to add them up. All right, there's 4 bromines, which each have 7 based on the periodic table. Here's bromine right here. So that's going to be 28, and it's bonded with a carbon, so that's 4. So we know immediately that one has 32. So let's see if anything else does. PCl3, chlorine is bringing 7, and you have 3 of them, that's 21. Phosphorus is 5, so that's going to be 26. So that's not it. Nitrogen brings 5, and each hydrogen brings 1. All right, here's nitrogen, here's hydrogen. So we're only talking 8 there. HCN, you're getting 1 from hydrogen, 4 from carbon, and 5 from nitrogen, so that's only 10. And then CO32-, you get 6 from each oxygen, so that's 18, plus another 4 from carbon. So that's 22 plus an extra 2, so that's still only 24. So the only one that has 32 is going to be CBR4, just number 1. All right, let's keep moving. All right, so again, we have another list. We have CO2, which is linear with 2 double bonds, CCl4, which is tetrahedral, CH4, which is also tetrahedral with no lone pairs around the central atom, and no lone pairs around the outside atoms. SO3, which is trigonal planar, takes a double bond between sulfur and one of the oxygens to make it work. And PCl3, which is trigonal pyramidal and has a lone pair on the phosphorus. So letter 8, which molecule has only one double bond? All right, or the only one with a double bond. So again, you're thinking about your cons, C-O-N-S, and it's going to have 2 of those elements. So we got a C and an O. We have a C and a CCl, so that won't work. A C and an H, that won't work. An S and an O, that could work. And a PCl3, that couldn't work. So we've narrowed it down to CO2 and SO3 minus. Both of these are going to have double bonds. The question is, which one has only one? That's going to be SO3. When you draw SO3 out, you have 24 electrons to work with. You do all single bonds between sulfur and oxygen. You fill your oxygen octets. Sulfur is not happy at that point, but you've used all your electrons. So you have to turn one of your lone pairs into a bonding pair. The molecule that displays polarity, so you can just base that off your chart. This one is a little bit different, doesn't talk to us about polarity, but I can use it to help you. So we talked about 2 shapes that are always polar, trigonal pyramidal and bent. Okay, so if you have one of those 2 shapes, it's always polar. If it's linear, if it's trigonal planar, or if it's tetrahedral, you have to make a decision. Are all the atoms around the central atom the same, or are they different? All right, so first off, linear, but everything around the central atom is the same, so nonpolar. Tetrahedral for both of these guys, but everything around the central atom is the same, so nonpolar. Trigonal planar, but everything around the central atom is the same, so nonpolar. So the only one that's polar is going to be letter E, because in this situation, it's the only one with a lone pair. And as soon as you have a lone pair around the central atom, you're going to have a polar compound. All right, and then the molecule that has trigonal pyramidal geometry, that's also going to be letter E. Okay, and we've kind of hit that a couple times. Linear, tetrahedral, tetrahedral, trigonal planar. This is the only one with a lone pair, therefore it's your trigonal pyramidal. 3 atoms around the central atom. Ready? So for number 11, which of these has resonance structures? Okay, so remember, resonance structure means that you can draw the atom multiple ways. Okay, so if it has a double and sometimes a triple bond, but mostly just a double bond, and you can move that double around within the structure, then that's going to be resonance. Okay, so here we have bent and all single bonds. Here, we're going to have a total of, 18 electrons. So the only way to make it work is to have 1 single bond and 1 double bond with the sulfur and then a lone pair. So this one is also going to be bent. Here we have linear. Okay. When you have OF2, that's going to be bent as well. And then PCl3 is trigonal pyramidal. Okay. So single, 2 doubles, so you can't really flip them in that situation. Single bonds, single bonds. So letter B is the only option that only has 1 double bond. So I could put the double bond between sulfur and either oxygen. I could flip it back and forth, and that is the definition of resonance. Okay, if I have multiple ways that I can draw the same structure. Number 12, the Lewis dot structure. For which of the following molecules shows only 1 pair of unshared valence electrons? So we should know the only Lewis dot structure really that has 1 pair of unshared electrons is usually trigonal pyramidal, every once in a while bent depending on the situation. So CCl2 is going to be linear, N2 is going to be linear. I know that because those are both Brinkelhoffs. Those are two of the same element bonded to each other. Linear is the only shape that they can form. All right, PCl3 is trigonal pyramidal. You'll notice PCl3 is used a lot in this test. So as you were taking the test, if you drew PCl3 every single time you had a question on it, that's just not very good use of your time. Okay, we try to put the same ones in the test over and over. So once you draw them once, you don't have to do it again, but you have to be able to recognize that. So PCl3 is trigonal pyramidal. That means it is going to have one unshared pair of valence electrons. CCl4 is tetrahedral, and H2O2. H2O2 is actually a kind of a unique structure. Your two oxygens are going to be double bonded to each other, and they're going to be single bonded to each of the hydrogens. Okay, and then you'll also have a lone pair involved in there. All right, that's hydrogen peroxide is what that one is. Okay, so the only one that's going to have one lone pair around the central atom is going to be PCl3. All right, number 13. Which of the following has trigonal planar configuration? All right, PCl3 or BCl3. This one is actually trigonal pyramidal. Remember, boron is an exception and only needs 6 valence electrons to be happy. So it's going to form a single bond with each chlorine and everyone will be good to go. CHCl3, carbon's going to be in the middle. It's going to form single bonds with hydrogen and 3 chlorines. So you have tetrahedral, and then you have PCl3, which is going to be trigonal pyramidal because it has a lone pair. So it might be kind of confusing to try to figure out which one it is between BCl3 and PCl3. But here's the deal. PCl3 has a lone pair, which means it's going to push the bonding pairs down. So that's going to be trigonal pyramidal. Whereas BCl3, because boron is happy with only 6 electrons, you just have 3 bonding pairs. They can spread out further within the same triangular plane. So it's going to have trigonal planar configuration. So it's going to be one only. All right, number 14, which of the following most accurately describes the bond between magnesium and fluorine in MgF2? All right, so remember, magnesium is over here on the metal side, fluorine is over here on the non-metal side, so this is an ionic bond. In an ionic bond, you have the transfer of electrons. So magnesium is going to give electrons away to fluorine. Magnesium's in group 2A, so it has 2 electrons to give away. Fluorine's in group 7A, and it only needs 1. Okay, so this kind of goes to, hopefully you have a better understanding of this based on what we've just done over the past few days. Okay, you have to have 2 fluorines with a -1 charge to balance out 1 magnesium with a +2 charge. Okay, so if we were to do a formula, we would swap and drop, and we'd end up with MgF2. Well, remember, that means that there are 2 fluorines and 1 magnesium. So if magnesium has 2 electrons to give away and each fluorine only needs 1 more to be happy, magnesium is going to give 1 electron to each fluorine. By doing that, each fluorine has a full shell and it's happy, and magnesium can drop down to a lower energy level and be happy. Okay? So this is what we're going for here. This is an ionic bond, okay, where magnesium is giving away 2 electrons, 1 to each fluorine. Okay? You should have been able to knock out letter A immediately because you know it's a metal and a nonmetal, so it cannot be covalent. All right, number 15, which of the following is most likely to form covalent? Again, you have to recognize that ionic is a metal and a nonmetal, covalent is 2 nonmetals. If you know that, then you know this one's no good, RbO2, because Rb is a metal, oxygen's a nonmetal, so it has to be ionic. Okay, CaCl2, calcium's a metal, chlorine's a nonmetal. Again, that one has to be ionic. CS2, all right, carbon's a nonmetal, sulfur's a nonmetal, this is a covalent compound because it's only between nonmetals. MgO, magnesium's a metal, oxygen's a nonmetal, so that one has to be ionic. And then it says brass, an alloy of copper and zinc. Okay, copper and zinc, here is copper, here is zinc. Those are two metals that are being mixed together. Okay, that's what we call an alloy, like stainless steel or something like that. So if we're talking about two metals, well, then that's going to be a version of metallic bonding. So the only one that can be covalent bonding is the one with two nonmetals. All right, and that's going to be CS2. All right, number 16. This one was very disappointing to me that people miss this question at all. It says, which of the following is a Brinkelhoff? Okay, a diatomic Brinkelhoff. Diatomic just means two atoms bonded together. Remember, we said this word right here, Brinkelhoff. That is a goofy made-up word that stands for elements that are always bonded together. So bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Okay, all of those elements are always bonded together. That's why we call them Brinkelhoffs. Again, I don't understand how anybody missed this question. There's only one option here that is made up of this particular word, two elements bonded together. You have SF6. Well, heck, that can't be it because S is not even in Brinkelhoff. CO2. Okay, again, that doesn't work because carbon's not in Brinkelhoff. H2O. I'll give you this. Both of those are in Brinkelhoff. But when we say diatomic, we mean two of the same atom. We have two hydrogens, but we also have an oxygen attached, so that can't work. F2 and HF. Again, you have a hydrogen and you have a fluorine in the Brinkelhoff, but diatomic means two of the same atom. These are two different atoms. All right. The clear answer is F2. Okay, there should be no reason that you picked anything else. It's asking you which one of the choices is one of these guys. A Brinkelhoff is just two of these elements bonded to each other. F2, O2, H2, Cl2, N2, I2, Br2. Okay, so if we miss that one, we got to do a better job of just kind of paying attention to what we're being asked. All right, so we got CCl4, CO2, again, a bunch of repeats here. So if you were drawing them every single time, it's just not really good use of our time. CCl4 is tetrahedral, CO2 is linear, PCl3 is trigonal pyramidal with a lone pair, HCl is linear. As we know, anything that involves just two atoms is going to be, and H2S is bent because you're going to have two lone pairs off the sulfur. All right. So we got these here choices. It says, which of the following bond angles describes the bond angle in SO3? Okay. Sorry, I kind of skipped this one. Didn't tell you the answer. My bad. It says, which of the following does not describe any of the molecules above? So I just went through tetrahedral, linear, trigonal pyramidal, linear, bent. The only thing that we didn't talk about was trigonal planar. So you don't have one up there that is trigonal planar. You don't have one that has three atoms around the central atom but has a double bond. All right, number 18, which of the following bond angles best describes the bond angles in SO3? SO3 is trigonal planar. Okay, if you look at trigonal planar right here, there's two different ways that it can be done, but it's going to have a bond angle of 120. Okay, that is the bond angle that accompanies trigonal planar. And again, that was written directly on the board or directly on your chart, depending on your situation. So all you had to do was draw SO3, which has been asked multiple times on the test, realize it has a double bond, which makes it trigonal planar, and that means every bond angle is 120. All right. Number 19, which of the following correctly shows how carbon and hydrogen form a bond? All right, so carbon and hydrogen, we know this is going to be covalent because we have a nonmetal and we have hydrogen. So that means we have the sharing of electrons, not the transfer. So we shouldn't have any charges or we shouldn't have any arrows. So you know immediately these two guys are out, okay, because those represent ionic bonds. So we're at this point right here. And you know D can't be right because you know hydrogen only has one valence electron and it only needs 2 to be happy, so hydrogen can only bond one time. So the only answer you have left is C. Okay, I can't really highlight this one because it's part of a text box, but C would be your correct answer in this situation. Didn't like that at all, did it? Okay. Number 20 says, which of the following represents the Lewis structure of ammonia NH3? So again, NH3 is going to be covalent because you have 2 nonmetals. All right. This one is also a little bit pretty simple to knock out because N is contributing 5 electrons. This is right here. Each hydrogen is contributing 1, and you have 3 of them. So that's 8 total electrons. Okay. So you know D is out immediately because it has way more than 8 electrons. All right. You know C is out because there are clearly 4 H's there, and the formula is NH3. So that just leaves you with A and B. Okay. So again, everyone has to be happy in this situation, but hydrogen can only bond one time. Hydrogen only needs 2 to be happy. So that's going to knock out letter B because we have one of our hydrogens trying to form a double bond. It's not part of your cons, it can't do that. So that just leaves us with A. Nitrogen is going to share a pair with each hydrogen and then have a lone pair on top to complete its octet. All right? Okay, so that finishes up the multiple choice. This one right here obviously is going to depend a lot on your chart. So you have to draw the Lewis structure, identify the geometry, determine the bond angles, and label as polar or nonpolar. Okay, so CCl4, that is a grand total of 32 electrons. So you're going to put carbon in the middle. You're going to form a single bond to all your chlorines to make carbon happy. That's going to only take up 8 electrons, so you have 24 more. You're going to fill your octets of chlorine. So it's going to be tetrahedral. Bond angles for tetrahedral are 109, and all the atoms around the central atom are the same. So it's going to be nonpolar. Okay, so CCl4 is going to look like this right here. Okay, so there's CCl4 right there. Okay. All right, SO2. SO2 is a little trickier. You're dealing with 18 electrons, okay? If you put sulfur in the middle, do all single bonds, and then fill your octets, then you're not going to use up all your electrons, and not everyone's going to be happy, okay? So what you're going to have to do in this situation is you're going to have to form a double bond, okay? So let's look at SO2. All right, so in SO2, if we're talking just regular SO2, we're not talking about a charged version of SO2, okay, then this one is going to be linear, okay, because you're going to form a double bond between sulfur and each oxygen, okay, and you can put a lone pair on sulfur, so that's one way to do it. Probably the more likely way that you did it was this one right here, okay, because we didn't talk too much about sulfur being an expanded octet. So what you did was you took one of the bonding pairs, or the lone pairs from oxygen, you made it a bonding pair. So there's a single bond between sulfur and one oxygen, and then there's a double bond between sulfur and the other oxygen, and a lone pair on the sulfur. So what that means is that you're going to have a bent shape, because you have 2 atoms around the central atom, and you have a lone pair. If it's bent, then we said the bond angle was 104.5 degrees, and we know if it's bent, it's always polar. All right, H2O is water, so you're only dealing with 8 total electrons. So you're going to put oxygen in the middle, form a single bond between oxygen and each hydrogen. That makes each hydrogen happy, but you have 4 more electrons, so you have to put 2 lone pairs on your oxygen. It's going to look like this right here. There we go. Okay. There's the Lewis structure for water. Single bonds, 2 lone pairs on your oxygen. Those lone pairs are going to push your bonding pairs down, okay, and you're going to end up with a bent shape. That means the bond angles again are going to be 104.5, and we know if it's bent, it's always polar. All right, in F3, you have 21 electrons from the fluorine plus another 5, so 26 total. Put your nitrogen in the middle, form all single bonds. Fill your fluorines octets. Your fluorines are all happy, but you've only used 24 of your 26 electrons, so you're going to put a lone pair of nitrogen, which means you're going to get trigonal pyramidal. It's going to look like this. Okay, there we go. All right, so nitrogen in the middle, single, single, single. Fill your fluorines octets, and then the lone pair needs to go on nitrogen. All right, so trigonal pyramidal. If it's trigonal pyramidal, we said that our bond angles would be 107, and then again, because of the lone pair, it's going to be polar. All right, carbon dioxide, CO2, that is 4 electrons. It's another 12, so 16 total. If you put your carbon in the middle and single bond to your oxygens and then fill the octets, you've made your oxygen happy, but your carbon's unhappy. So remember cons, C-O-N-S, you got 2 of them. So you're going to have to mark out 2 of your lone pairs and make them bonding pairs so that we get something that looks like this right here. Okay, that'll work. So you're going to form a double bond between carbon and each oxygen, and then you're going to put the 2 lone pairs out on the oxygens. All right. If we have 2 atoms around the central atom and no lone pairs, 180 degrees is going to be the bond angle we're looking for. So this is going to be linear. Okay. So linear, 180 degrees on the bond angle, and everything around the central atom is the same, so it's going to be nonpolar. Finally, we have an ion here at the end, NO3 minus. So you're getting 18 electrons from the oxygens, you're getting another 5 from the nitrogen, and then the negative charge tells us that we're getting an extra one. So we're talking about 24 total electrons. All right, so let's see, without me explaining it to you, let's see what that one looks like. All right, so here's going to be NO3 minus, okay. I like this one because it shows you all the resonance structures. So NO3 minus, you can't just do single bonds and put a lone pair because you don't have enough electrons to do that. So you have to take one of your lone pairs from oxygen and make it a bonding pair, and then you can make everyone happy. So this shows you all 3 of the different ways that NO3 can be drawn. Okay, we can have a lone pair between nitrogen and this oxygen, the top oxygen, or the oxygen on the other side. These are all considered correct. No matter how you squeeze it, you're going to have 3 atoms around the central atom with a double bond and no lone pairs. So that is trigonal planar. Trigonal planar has a bond angle of 120, and because everything around the central atom is the same, it's going to be nonpolar. All right, number 7 says draw the Lewis structure for BF3 and CO32 minus. Explain why one shows resonance and the other doesn't. All right, so let's look real quickly. BF3, you got to remember, is an exception. So BF3, boron is happy with only 6 electrons. So boron is going to form a single bond with each fluorine and doesn't need a lone pair. Okay, there's no way to have resonance for this structure because it's all single bonds. There's not another way that you could draw it. There's not a way that you could manipulate the bonds. So if you can't manipulate the bonds, then you can't have any resonance. And CO3 or CO2 3 minus, oh gosh. On the other hand, okay, you have this situation right here. Okay, the only way to make this work, this is actually better. I like that one a little better. Well, no, that's not good. Too many double bonds on that one. There we go. The only way to actually make this work is for you to, there we go. Okay, take one of your bonding pairs from one of the oxygens, make it a double bond. This one has resonance because I could have used this double bond, or this one, this lone pair to make a double bond. I could have stolen a lone pair from the top oxygen and made a double bond, or I could have stolen a lone pair from the far oxygen to make a double bond. That's what makes it resonance. Okay, you can't have a resonance structure really very often without having a double bond. Sometimes with a single bond, if you have elements on different sides of the or different elements on the sides of the central atom, but for the most part, it's going to require a multiple bond. Okay, so that's why. Okay, CO3 2- shows resonance because it has a multiple bond that can be moved around, whereas BF3 is all single bonds. All right, so we had some characteristics up here, and we had our 3 types of bonding: metallic, ionic, covalent. So under metallic, you should have had electron C model. Okay, it's the only one where the electrons float around like fish in the sea. And you should have had that as conductive as a solid. All right, so if you think back to the lab we did with the homemade conductivity meter with the battery and the Christmas light, and when you touch the iron and you touch the foil, it caused your light bulb to light up. So those two should go right here. Under ionic, we have electrons that are transferred from our metal to our nonmetal. Remember, the only ionic compounds that conducted electricity were in solution. And we talked about how ionic compounds have super high melting points because of the crystal lattice structure. So you have to break all of the bonds in that crystal lattice to make them actually melt. Okay. And then covalent, this is when electrons, hush, hey, hush. This is when electrons are shared. Okay, so this is going to be your nonmetals. They're going to share electrons. Covalent bonds are not near as strong, so they're going to have very low melting points. Okay, so those should have gone here. I didn't worry too much about where you put brittle because we didn't talk about it that much. I'm not going to really go over the bonus with you too much. Realize that this one right here has to have an expanded octet. In other words, Te can hold more than 8 electrons. For number 2, why would you expect I3 - 1 to be polar or nonpolar? You should have said that it is nonpolar because we're dealing with all iodine. So if we're dealing with all of the same electron, then they're not going to have differences in electronegativity, and that's what causes polarity. So if they all have the same electronegativity, it's going to be nonpolar. Bonus number 3 wanted to know, why is it that you can make PCl3, PCl5, and NCl3, but you can't make NCl5? Well, here's the reason. PCl3 and NCl3, those are pretty easy. Those are both going to be trigonal pyramidal. You just slap a lone pair on your central atom. PCl5, because phosphorus is lower on the periodic table and has ventured into the 3rd energy level, it can be an expanded octet, okay, because it's jumped into that 3rd energy level and it has more places to bond. Nitrogen, on the other hand, is only in the 2nd energy level, so there's no way for it to be an expanded octet because it can't drop down into the 1s, because the 1s only bonds one time. Okay, so that's the reason that there's no such thing as NCl5. All right. And then number 4, the bond lengths of a nitrate ion are identical. Justify why. So if you remember, we said a nitrate ion, thought I might still have it up here, but I don't, but we'll fix it real quickly. All right. Nitrate ion is the one that has resonance, okay? Anything that has resonance, any compound that has resonance, the bond angles are going to be the same because they're an average. So you never know where the double bond is going to be. So because you don't know that, you consider all the bonds to be an average of each other. And if they're an average of each other, they're all going to be the same length. Okay, so that's going to be the answer to bonus number 4. All right, so hopefully that clears up some issues that you had, and going back over this and answering some new questions has helped you out.